To start, we're going to begin in Flotherm Pack, which is an online tool for generating thermal representations of packages for use in Flotherm. We'll log into the tool and go to the New Package option, and here we can see the various JEDEC package models available to select from. For this example, we'll be using the wire bond plastic ball grid array. This will take us into the wizard where we'll be guided through the package creation process. We give the package a name and then select the package with the closest matching size to the package we want from the standard sizes. We apply a power of 5 watts. We then step through the wizard providing Flotherm Pack with everything we know about the internal construction. All of these settings can and will be changed shortly when we reach the design sheet. Here we can see all the inputs for the construction of this package. Before changing anything, a good first step is to generate a preview so the device can be visualized in its current state. An online VRML viewer can be used to upload the WRL file so a 3D model is generated and can be interrogated. This is the state of the unmodified package using all the default settings. Switching back to Flotherm Pack, some modifications have been made to the package, such as the BGA outline and the removal of the central ball region. Die and encapsulant changes have also been made. The solder ball size and spacing have also been made larger. Uploading the modified file to the 3D viewer, we can see the changes to the geometry. So Flotherm Pack allows us to adjust geometric and material properties from a web interface before we've even started Flotherm. The other great advantage of Flotherm Pack is the generation of compact IC thermal models. Two types of compact models can be created, 2-resistor and DELPHI. The jobs need to be submitted, and this process takes on the order of minutes to complete. Clicking through to the 2-resistor model shows us the junction to case and junction to board thermal resistances derived for our custom BGA. The DELPHI model has a resistance table with additional nodes and is considered superior to a 2-resistor model. The top inner and outer and bottom inner and outer nodes can be seen with the thermal resistances between them. We'll download all three models, 2R, DELPHI and Detailed, so we can see the differences over in Flotherm. Importing the downloaded detailed PDML into Flotherm, we can see the primitives which have been used to construct the package. Here in wireframe, we can see the internal construction. Switching to solid mode and making the encapsulant transparent allows us to see the structure of the device. The package can be dragged into the library where it will be available for future use. This is particularly useful when swapping out components on imported PCBs. When boards are imported, the packages come in as the simple block representation, which is very inaccurate from a simulation standpoint. By replacing the simple block representation with a library item, we are greatly increasing the fidelity and accuracy of the simulation. The color has changed to gray, denoting a detailed package model. The same can be done with the 2R and DELPHI models. By downloading and saving to the library, they can be stored for reuse across the organization. The final benefit of using Flotherm Pack is the ability to add the device we've created to a JEDEC standard test environment. We click on the Add Test option and then step through the options. As this is a fairly large package, the large board option is used with a high conductivity PCB. We do not want the thermal vias. Here we can see the 4 types of tests that can be created: θJA, JMA, JB and JC. All of these test environments conform to the JEDEC 51 standard for reporting thermal characteristics. The test PDML is downloaded for use in Flotherm where it can be imported. Once in Flotherm, the model can be checked with regards to material properties, thermal loads and solver settings. The still air test chamber is a 1-foot cubed volume with the device on a PCB in the center. We can expand out the testing package and confirm it's in the correct location and orientation. Gravity can be seen in the negative z direction. To check the material properties, we can select items in the Project Manager and check the attachments. For example, on the die, we can see silicon as the material, and switching to the die source, we can see the die heat attribute corresponding to a 5-watt load. Any object can have its attachments checked, such as the PCB traces. The Library Manager controls all of the attributes which are collected and managed. Properties such as the conductivity, density, and specific heat can be modified. Let's now check the computational mesh. To do this, we go normal to the screen and press G on the keyboard. Flotherm uses a structured Cartesian grid to resolve geometry, and this can be toggled on and off quickly. The grid can be updated instantaneously, such as the base system mesh, by adjusting the maximum size value to make the cells smaller. Grid constraints are attributes that can be added to project items to control the mesh size. If we desire a finer mesh in the Z direction, we can adjust the grid size around the package. Note how the mesh updates without having to run a separate mesher. The Information button quickly outlines the attributes assigned to every object and includes a cumulative power total also. The Model Setup tab shows the project settings, such as the radiation solver and that the transient solver is off. The ambient temperature is set to 20 degrees C with air as the working fluid. We're now ready to solve this model, which is just a case of going to Solve and Solve. The solution residuals will appear in a new tab, and we can watch these as the model starts to converge. We want the residuals to tend towards 1, which signifies a converged CFD solution. This model takes approximately 5 minutes to complete. For this next section, we'll look at how to examine visual and numerical results in Flotherm for package level analysis. The post-processing is conducted inside the main UI of Flotherm in Analyze mode. Let's hide the outer walls of the still air test chamber so we can see the test package on the PCB in the center of the volume. Zooming in, we can see the BGA on the JEDEC test board with gravity in the negative Z direction. Let's first create a surface plot on the JEDEC test PCB, and we can see a hotspot around the BGA. The scalar legend will auto-range to give a smooth gradient between min-max temperatures. We can see a max PCB temperature of 63.7 degrees C. Going to wireframe mode shows the hotspot clearly under the BGA. Now let's turn on the BGA surface plot, and you can see the legend change to account for the new min-max. Surface plot annotations have been created to show where the min-max temperatures on the model are. Turning off the PCB shows where the hottest and coolest spots on the package are. We can see a range from 104 to 51 degrees C. Let's now hide the encapsulant so we can see the die within the BGA. We can clearly see the 104 degrees C hotspot on the die, which is the junction temperature and the hottest volume in the project. We can use the annotation mode to mouse over anywhere to extract solid temperatures. Let's now take a look at the plane plots, which are 2D slices through the project. Here we're plotting temperature again, and we can see a plume of hot air rising against gravity. We can again use Annotate mode to check fluid and solid temperatures where our cursor is. Planes can also show airspeed. This velocity is generated through natural convection only. Vectors can also be plotted, showing magnitude and direction. A slice through the center of the device shows the solid temperature. We can also plot solid conductivity to double-check our inputs. We can visualize the airflow using particle plots, which are the air streamlines within the domain. These can be animated to show the dynamic airflow. Finally, we can extract numerical results from any item in the project manager. We show the tables window, then select the object of interest in the project manager. For example, if we select the die, we can see the maximum solid-solid temperature of 103.84 degrees C. This is our junction temperature. We can also see the power load of 5 watts, which we applied back in Flotherm Pack. Taking the junction temperature, subtracting the ambient of 20 C and dividing by the power of 5 watts gives us 16.8 degrees C per watt, which is our theta JA JEDEC metric. We can add any other objects we desire into the tables window to give us a quick summary for comparison purposes. Heat loss due to conduction, convection and radiation can be quantified in this way. Results can be exported to Excel for further post-processing. In this final section of the Flotherm package level demo, we'll look at variant analysis using the Flotherm Command Center. The Command Center allows for automated variants based on all the inputs and outputs defined in the base project. The workflow can be seen in the tabs along the bottom, and we first define input variables. Let's first adjust the die source size. We're not 100% sure on the active area of the die, so we can use Command Center to understand the model sensitivity. We can tick on the absolute X and Y size of the die source. This populates the variables list where we can change the X value to a design parameter. We now need to give the min-max bounds for the size, which we'll set to 6 and 11.5 millimeters. We want the Y value to follow the X size, so we set this to a dependent variable, then select the X value in the equation prompt. To ensure the heat source is centered on the die, we need to adjust the X and Y position on the die surface. We do this by making the position a dependent variable also, and changing the dependency equation to half the die size for X and Y absolute positions. Although we have 4 inputs, we only actually have one design parameter, the X die size. The last input variable will be the die attached material conductivity, as we're not 100% sure on the accuracy of the datasheet value. We go to the material properties and select the thermal conductivity as another input variable. We'll adjust the range to 1 to 2.5 watts per meter Kelvin. On the Output Variable tab, we'll select the junction temperature as the value of interest and include it in the cost function. This will now report the TJ max for all scenarios. On the Scenario Table tab, we can see the base project we solved with all the initial values. The solution status is green, indicating a converged solution. Using the Create Scenarios option, we'll use Design of Experiments. We can see the input variables we just defined with the min-max ranges. Let's create 10 experiments which cover the full range of inputs. The scenario table is populated with our 10 points. Going to the scenario viewer, we can confirm that the heat source changes size and it's centered on the die. The die attached conductivity is reported in the scenario table. As we need to solve the 10 designs, we can speed this up by activating the parallel solver. Here I have 4 concurrent solves with 4 cores each enabled. We'll click Solve and wait for the jobs to finish. Going to the scenario viewer, we can plot surface temperatures for each variant, paying close attention to the max temperature changing. The response surface viewer allows us to see the 3D relationship between the source size versus conductivity versus junction temperature. We can see a mostly linear relationship. This graph can be used to interpolate points off the curve if needed. The final feature of the Command Center for packages is the Trista calibration process. Trista measurements can be imported and then the simulated structure function made to match the measured structure function. This is done by varying uncertain geometric and simulation parameters until the curves match. This allows for the generation of very accurate package thermal models for use downstream or to provide to customers.